Hi, I am Tuseeta Banerjee and I am a research scientist working in the machine learning team at Wolfram Research. And today I'll be talking about importing neural networks with ONNX. And it just talks about all the difficulties that we had in the last 1 year or so importing models manually and why an automated tool is required for importing networks. Thank you.
Hi, so I am Tuseeta and I work as a research scientist in the machine learning team at Wolfram Research. So I'm presenting a work which is mostly done by my coworkers. I'm just trying to take over the project right now. So with my other coworkers, so it's mostly done by James and Matteo. So just giving the credits where it's due. And I will try to present it to the best of my abilities and also talk about why this project is important in our team. So I realized when I was presenting this that we do not have any other talks that introduce all the models in the repository. But the title of the talk was already decided that it's going to be ONNX importer, so I just thought I'll hijack it a bit and talk about all the models that we added since 12. So it's not since last tech conference, but it's since last release cycle. So it's since 12. We have added these models in the repository. Feel free to go ahead and check them out. They are the newer models. I will talk about one important model and try to say why we need ONNX or what difficulties we faced trying to get that model in the repository. So there are no automatic tools anymore. So we had a MXNet importer, and we did have an unofficial Torch importer. But as research progressed, most of the models are developed in PyTorch and TensorFlow. So if you have to get any external model into our framework, we need either a PyTorch or a TensorFlow converter or do it by hand. Doing it by hand is extremely time consuming. It is very erroneous and it's tedious. So you make the architecture, you take the weights, you parse the weights, you link the weights to the architecture, and few of these neural nets have around 800 to 900 layers, the newer ones. And doing this kind of thing by hand is not a fun thing to do. I have done a few of them, and it was not the best time. So that's why we were like, oh, we need an automatic converter, and that's why we are trying to build ONNX. So this is sort of the code of this is not here with me. So Bob made this code where it shows the number of models that have been added since the repository, since the neural net repository started. You can see there is a little bit like a less increase in the growth, but we have continuously added several models to the repository. One of the explanation why there are fewer models is what we started doing since 12. We introduced something called parameterized net models, which means many of these models, which slightly differ in architecture or differ in the data set which it was trained on, they all come under same class. So if you saw the repository before, you would have seen like there are like 8 or 10 models of cycle GANs doing zebra to horse, horse to zebra, apple to orange or whatnot. But right now, all of those similar models will be in one name, so that there's not like an exponential growth, and you can see it's more organized per se. So let's go ahead and see one of them. So the mobile net, which was image classification network that was introduced in 2018, if I am correct, or 18, yeah. So this brings down the size of image classification networks by around anywhere between 1/10 to 1/100th. And they are also faster because they have fewer parameters. And they were, like it says, they were supposed to run on handheld devices. That's why they were made. So these kind of networks have a lot of different parameters. So again, if we just published them like we did before, there would be 22 models suddenly added to the repository, and it just made it longer and longer. So what we came up is the parameterized net model. I think this is a good place to show the parameterized net model machinery. You will find some of these functions in the neural net repository page of that particular model, but some of them are not there. So I just thought I will show some of the options that's not mentioned in the notebooks. So you can find out all the parameters. You can find the default variant. So if you just query net model of this name, you would get the default variant. So without the default variant, here it just shows which one is the default variant. So for many of these, all the combinations will not be available, because as you can see, if there were all of them, I think you would have gotten, I think there are 5 and 5, 25 or 30 of these. I think only 22, not I think, I know there are only 22 available. So for things that's there, it will return you the particular model. For combinations that are not allowed, if you just try to get all the variants, it will just fail with the appropriate message saying that that combination is not allowed. So this is something which is not there in the example page. So I thought this is an important example that I can show. But yeah, so you can just pick a non-default one by just changing the parameters. The default one was 1.4 and 224, so I just pick a non-default one. Similarly, you can pick a non-default uninitialized net. That sort of machinery is still there, and then you just predict a non-default one, and it gives like normal prediction, which is, this is like the image which is there in all image classification problems. So that's just introducing the parameterized net models. There are even greater use of these parameterized net models. So if you see the BPE model, it has subword embeddings for various languages of different vocab size and different dimensions of embedded vector, and there is no possible way that we could just have like an exponent. There are like 275 languages here, that we could have so many different languages scattered in the neural net repository page. So that's why, again, justification of why the parameterized net model machinery is required. So again, similarly, you have, it's just a similar example where you can get like non-default untrained net. You can get the encoder. This is just an example of the BPE model, so we can just go over it quickly. So BPE just converts the segment into words or subwords depending upon the vocabulary that it has, and it will output an integer for each token. So the token could be a word or could be a subword. So that might not be just 1:1 ratio here. So again, it could tokenize in any language. So this is like a thing written for different languages, and here it just compares it to different languages. So I don't think so. I just know Bengali. I think that's the only one which I contributed in this example. The rest of it was, again, from different, as you know, we have a very varied, more global company. So I guess everybody got one. Like we collected examples, but I know I gave the Bengali one. So it's something for the brain. I wasn't expecting that question though. So yeah, but okay, so now I come to the main part of it, is like, what's the problem with hand conversion and why we need ONNX? So here is a very famous model that was released on, I remember this date, it was released on 14th February 2019. And so, yes, I saw that, Timothy. But yeah, it was released on 14th Feb 2019, and this is what the model is. And we had a hard, or at least I had a hard time trying to convert this model by hand. So again, this is also a parameterized net model. There was feature extraction, there's language modeling, and different sizes of the net. So you can, all in all, when it comes to the repository, you can pick them, and then it's all pretty and nice, and the model will come, like whatever you ask for it, it will just return that thing. But behind the scenes, like first let me just describe the model here. So we have this net encoder function. So it's the function net encoder, not any of the built-in one. And creating this function also, so it has all the dirty pre-processing that GPT-2 model had. So it has BPE subword tokens, and then it also has a conversion from UTF-8 to like the ASCII codes, and there is this part, and then there is an extra pre-processing part to the BPE subword tokens, but all of it is covered in this like small, nice-looking net encoder function. You can definitely query, keep on extracting from there, so that if you want to modify the net encoder function, you can as well do that. But yeah, that's all there in that encoder function. That's all the pre-processing. And you can also query for different positions and all. But in general, it does things very similar to the BPE encoder. It will convert a string into a list of tokens. So that's what it is doing. And it also has another thing. It needs to give the positional index here. So it also gives something like 1, 2, 3, 4, 5, 6. It's like shows the position the position of the token in the string. So again, a lookup is done. So ultimately, it gives a vector of size 768. Yeah, I don't know if I took the large one or the smaller one, but it is 1024 or 768, depending upon the size of the model that I am using. And this is what you see. Like these are the embeddings, and then you can find out. So this is the embedding part of it. So you have two embeddings, the input, which gives the tokens, the positional embeddings, and then you just add them together and get the embedding part of the architecture. Then what you have is what is a new sort of architectural paradigm that's called transformers, which were introduced in a paper called All You Need Is Attention. And it had two different things, an encoder and a decoder. So GPT-2 has what's called the transformer decoder, and again another equally famous NLP model called BERT has what's called the transformer encoder. The difference between the two is causal masking versus non-causal masking. So this is what's the causal attention. So it always looks towards it looks forward in time. So this is what GPT-2 has. And BERT has self-attention, so it looks both ways in time. So anyway, I think I will run out of time if I keep describing the architecture. But the take-home message was doing this 800 or 1,000 layer network by hand was not a happy job. So what it was is like you have to create the architecture. So this is the code that's creating the architecture. You keep adding the model parameters. Then you import the weights. So this one was just importing it with external evaluate. And then get the weights, then parse them by hand. So this is where I parse the weights by hand, do the replacements by hand, and then finally you get the network. So that's why we were like, no, we need ONNX so that we don't have to do this manual conversion every time we get a famous model. Again, we also could not, like, it was not a fast process. It takes quite some time to get all of this done and tested. The other thing about why we need a ONNX importer is that we don't really need to maintain a single converter for every kind. So we had a MXNet converter and a Torch converter. But again, if we have all of them together, there's nothing like it. So ONNX gives us that advantage. And then it has a model zoo. There are not a lot of models, but they are adding it. We also plan to add models. So there is a way where you can take a model from, they have these tutorials to convert models from, say, PyTorch or TensorFlow, and then convert it to ONNX. So even if a model is not there in the repository, in the model zoo, you can actually manually convert. You can actually follow those tutorials, convert it to ONNX, and then convert from ONNX to Wolfram language. Also, it gives access to tools like CoreML, where you can make your own apps. So that's something that is also good, so that you can have them in your handheld devices. And then there are other tools in ONNX. So there's Optimizer, there is runtimes, there are various hardware optimizations, there is also shape inferences. We can talk about them a little bit. But yeah, so this is what the official ONNX, this is from their site, so I just put the quotation mark. So it's an open format to represent deep learning models, and what the aim was to move models from, like, between state-of-the-art tools and choose which is best for them. And it was developed and supported, and they have this huge list of community partners who supports ONNX, and it's huge. It's maintained by a lot of different famous. It's actively developed by a lot of different people. So we think that this might not be one tool that might get scraped in future, because as the field progresses and it's so fast moving, you think that, okay, this is it, this is the framework where everybody will stick to, but in 2 or 3 years it changes. So I feel since it has gotten a lot of backup from different bigger companies, it will still continue. So that's why also we need to have something like this. So let's go ahead and describe the ONNX project. So the reason why I'm spending a lot of time in this is because ultimately what I'm going to show with importer is just import the model, and it will just take very less time. So it's better for me to sort of show or say what the project is all about. So again, it's Open Neural Network Exchange. I don't know why it is ONNE or not X before somebody asks that question. So the best thing is framework in interoperability. So you have most of the important frameworks, so Caffe2, CTNK, MXNet, and PyTorch, and also TensorFlow. So this is their symbol for ONNX. It shows like you can just convert from one framework to the other. There are also hardware optimization tools in ONNX, and also good visualization tools. That's also sometimes missing in many of these frameworks, is a good visualization tool. So they also provide visualization tools. Hardware optimization is not done yet. Like, we have not hooked that up, but there are runtimes and libraries that are designed to maximize the performance. So it's streamlining research to production, so if you want to use it. Yeah.
What does Amazon and Facebook use? What's their...
So Amazon, like the framework, if you're talking, again, not to be quoted, none of these frameworks are owned by any companies, but what is the company which provides the maximum developer to a certain production? Amazon does MXNet, and Facebook does PyTorch, and Google does TensorFlow. It's not official, but like they are all open frameworks, but that's where their majority of the developers contribute to maintaining the code of the frameworks.
And what about NVIDIA, since they're the main hardware provider?
I have seen NVIDIA use both PyTorch and TensorFlow. But in general, I read like a thing that mostly the company, like the business people, corporate, yeah. The corporate people are more using TensorFlow. There was a recent publication, and academic research is happening more in PyTorch. Personally, I feel PyTorch is a little bit easier to learn than TensorFlow, but TensorFlow also has Keras too, which came out. So I feel like that is also there. But whatever it is, it's like competing with each other. And we want models from both of them into our framework. And this is the way to go as a result. Like, that's why ONNX. So anyway, so I have 5 minutes of presentation time. Now I will actually go to the code. So each of them is it's a graph, and there's a computational graph model. So there's a protobuf that is stored in a protobuf format. So there are operators that are implemented. So each of the nodes can have one or more inputs and one or more outputs, and then the operators, they are implemented externally to the graph, and each of these operators should be portable across frameworks. So what we do is add operators that are compatible with Mathematica. So an ONNX operator has to have 1:1 correspondence with a layer or a bunch of layers in Mathematica, and that's what we are trying to build. So that's how this works. And the graph has nodes, which are the operations. It has the weights. That's how we'll import the model, and it has different metadata. So let's go ahead and demo it with an example. The reason why I did not push the notebook into Pathable is because this is not added to the builds yet. So as a result of which, I am just adding the Packlet directory and showing it to the demo, but it will be available in 12.1. So that's why it's just Packlet directory add, and it just works in my computer.
Available in when?
12.1 cycle.
You said 2021.
No, 12.1. Hopefully that comes out before 2021. Hopefully. So yeah, so Packlet directory add of that, and then you get this is just internal code to get the package, the Packlet. But here is where interesting stuff comes. So this is one of the internal function that takes the model, so that's in the protobuf format, the graphical format, and converts into Mathematica association. So this is what this function actually does. And you can just see the association and see, okay, so there's a graph, that's the graph that's built, and then each of the graph has nodes, like I said. So each of the nodes is an operator. What's an operator? It's like a layer in Mathematica, 1 or 2 layers. So that's how the graph looks like. So again, the key part of this association is a graph. So we can get we can query about the graph. That's the most important one. But other than that, there are other keys or other things that you can query. Most of them are like metadata. So you have the ONNX IR version, the offset version, so they keep updating the offset version, the producer name, where it came from, the version, the model name, domain. All of them might be there, or all of them, like, it could be there or could not be there. Let's see for this model. If I scroll down, so most of it is the graph, and it has all the operations and all the weights and stuff, and then you have all the metadata. So these are all the metadata that's available for this. And again, you can see it was done in Caffe 2. Some of it is absent as well. So okay, so that's mostly what's there in the association. Then you have the graph. The graph has different nodes. So these are the different nodes. I think I'll spend some time. So it's the first of the node. Again, a graph has all of the layers and all of the connections. I'm just taking the first one here. So this is the input. Like we said, we could have various inputs. So this one is the data. This one gives the weight and the biases of the layer. It's a convolution the operation type is convolution, so it's a convolution layer. And again, convolution layer has different parameters. So that's the stride of the convolution, that is 1 cross 1 stride. So it's a 2 cross 2 convolution with 1 cross 1 stride. Then you have padding. Then it gives you the kernel shape. So these are all the properties of the convolution layer that you would need to convert into a mathematical layer. And then, so this gives you the graphical connections. And the other thing you need to convert a model is the weights. So this gives you the weights. So this is the initializer, and this one gives you the weight of the model. So again, there are other things that you can get from the info. So these are all the dimensions of the layer. So that's a 22, like that's the size of those ImageNet images. That's the size that you start with, because your data would be 224 cross 224. And then, so this is, okay, and then you convert it to a 64 dimension. So that's the number of channels you have. But we don't really need to worry about all of this if you have your own model, and hopefully when it is imported, you can just do a ONNX import and give the name of the model. So I will skip the rest of the demos, which are very similar. So these are the demos that work. I have also shown, to be very honest, demos that don't work, because that means I need to work on those stuff. So this is more of a reminder for me what doesn't work. So sorry about this. I'll just skip through all the demos that work. And let's come to something that doesn't work. So these are all good things that work. Here the evil things start. Things don't work from here. And if you can see these, like, you will get some errors, like the reshape operator doesn't have batch dimensions, so we need to support these kind of. So we need to add batch dimensions to most of the operators, or try to find the corner cases how it will work. So that's what we are working on. So most of the thing you'll see, so there's batch dimension, broadcasting. These are the stuff that we need to add for few of these layers for these models to work. And that also brings us to future work. I thought this is a good way to introduce all the future work. The strengths, I think I have already mentioned, that it's being actively developed and it has big companies supporting it, and it supports many frameworks. The weaknesses of the ONNX thing is, I think mostly is like RNN is not actively supported. We are trying to give support to RNNs and things. Encoders and decoders, like the net encoder, net decoder that we have, the pre-processing and the post-processing step, I don't think so it's currently planned, but once you get the bigger architecture in, figuring out encoder and decoder is like 70%, 30, I think 60% of the work is done. You have to figure out the rest 40%. And also, these are the next steps that we were thinking of to add RNN support, the hyper network, but only static hypernets, and hookup to import. So like you saw, it was ONNX import. By 12.1, it should be just import, and then ONNX should be a format that is added. But it's like very, very like more future work. That was immediate future work. So the immediate future work is to add those batch dimensions and stuff. The second immediate was RNN. And then more in the future is hook up other tools like version and shape inference and model checkers, and the exporter that requires the protobuf exporter. So, and improving operator coverage is like a work which is in progress that keeps happening. So I think that's it, yeah. Yeah, welcome.